promising developments going on. Okay, of course, aside from the robotic space program, which has achieved some terrific successes, although it is being hamstrung in part by this kind of thinking, okay, although it has succeeded to a fair degree, because part of it is absolutely mission-driven. But outside of that, of course, the most promising development is SpaceX, and we're going to talk a lot about SpaceX tomorrow night, too. But in short, what you got there is somebody spending his money like it's his, because some of it is, not all of it. And he's doing some real stuff. And he's developing a substantial subset of the hardware that is needed to send humans to Mars. And he's showing that it can be done on in 1/3 the time at 1/10 the cost that had been previously deemed acceptable in the mainline aerospace industry. Okay, so he's making the Humans to Mars program much less of a stretch, so that the next time a politician says, humans to Mars, can we do it by the end of my second term? And can we do it for an amount of money that's not going to blow the budget to pieces? The answer is going to come back in a much more positive way than it has in the past. So that's where these two things intersect. But in the meantime, look, do we need this to go to Mars? No. All right. Okay. Many of you have heard my plan before, but many haven't. So those who have, forgive me if I just go through it. We need a heavy lift booster. We do. But that's not science fiction. This is not the future you're looking at here. This is 1970. Okay? This is 2 generations ago. We had this kind of capability. We can have it again. Okay? If you have it, heavy lift booster, here's your plan. You can launch to Mars every other year, which is an important point I'll come back to late in the talk. But in the first year, you use one of these boosters to throw an unmanned payload to Mars. It flies out to Mars. It takes 8 months to get to Mars using current chemical propulsion. That's the minimum energy trajectory. You can get there a little faster if you put on some electric gas. Then it uses an aerobrake to brake into Mars orbit. And after we check it out, we bring it into land, using the aeroshell to slow us down to subsonic speeds, pop a parachute, use rockets to come down soft, like we did with Viking in 1976. Here's the primary object landed. It's an Earth return vehicle. It's a little rocket ship for flying back to Earth. It's got a small cabin for supporting a crew of 4 coming back from Mars to Earth in the final leg of the mission. No one's in it now. 2 methane oxygen chemical propulsion stages, which, however, are unfueled. But in the lower stage tanks, some of them that are later going to contain methane, we've got about 6 tons of liquid hydrogen, so that after the landing, we telerobotically drive a small truck containing a 100 kilowatt nuclear reactor a few hundred yards away, turn it on, got some power, we pump in the Martian air, which is carbon dioxide gas. Carbon dioxide can react with hydrogen in the presence of the catalyst to produce this methane. Okay, that's natural gas, great fuel. And water, store the fuel, electrolyze the water, it gives us the oxygen. Hydrogen goes to make more methane, and then we run a 3rd reactor in which we take CO2 and we split it into carbon monoxide and oxygen. The oxygen we keep as useful oxidizer. The carbon monoxide we vent as waste. You can do that on Mars. There's no EPA there. That's one of the great reasons for going to Mars. Actually, if in a later stage in this process, we'll use that carbon monoxide to reduce Martian iron oxide, the red stuff that makes Mars red, produce steel. So that's how you make steel. Use carbon monoxide reacting with iron oxide. And steel is useful. But there you go. And you run this system, and at the end of it, you turn your 6 tons of hydrogen from Earth into 108 tons of methane oxygen bipropellant on the surface of Mars. Now, once again, later in the game, we now know there is water on Mars. We know that even at the equator, it's 5% of the soil by weight. And in other places, it can be 60% of the soil by weight. And there's even places where there's pure ice. We'll be able to extract water, and then we're going to need to bring the hydrogen. But while we do need to bring the hydrogen on the first couple of missions, it's still a leverage of 18 to 1. Okay, and there you go. So we've made the propellant on Mars. Next launch window, we launch 2 more boosters off the Cape. One shoots out another Earth return vehicle. The other shoots a habitat with a crew of 4 astronauts in it. they fly to Mars on a slightly faster trajectory, 6-month trajectory. 6 months is the right amount of time to go to Mars. You do not want to go faster. The reason is this. The 6-month trajectory to Mars, okay, or to be a little more technical for some people here in this audience who understand these words, the rest of you won't, but just deal with it. A C3 of 28 leaving Earth, okay, puts you on a 2-year free return trajectory. It will typically take about 6 months to get to Mars. If you decide not to stop at Mars, it'll take you out to about twice the Earth's distance from the Sun, and you'll loop back and you will reach the Earth's distance from the Sun, 1 AU, exactly 2 years after you left. If you try to, and therefore the Earth will be there to meet you when you get there. Is if you tried to get to Mars faster, you would, and you tried to do a free return, you would loop out further into the outer solar system, and you'd arrive back at 1 AU more than 2 years after you left. Maybe 2.2 years, 2.8 years, whatever. Unless you did it in such a way that you came back in exactly 3 years, you would miss the Earth again. So that's why the 2-year trajectory, which is the one that on average gets you to Mars in 6 months, is the right way to go. If you had a superior propulsion system like nuclear thermal rockets, you would not use it to go to Mars faster. You would use it to increase your payload, and therefore the safety of the mission by making your life support system quadruply redundant instead of doubly redundant, or something of this sort. And that, frankly, that does you much more good in any case than cutting 1 month off the flight time. So you go to Mars, 6 months, you get there, you fire a pyrotechnic, the cable is, well, we're not up to that part yet. Okay, here's the habitat. We got our return ride waiting for us to Mars, so we don't need an Imperial destroyer to get us there. We don't even need a Millennium Falcon. Here's typical layout of the hab. Little stateroom for each of 4 astronauts, science, exercise area, galley, and so forth. The center is your solar flare storm shelter. You pack that with provisions. That gives you the shielding to mask out solar flares. It does not give you the shielding to mask out cosmic rays, but that danger is overdrawn. And in fact, there's a scientist right here at this university who's been publishing papers saying cosmic rays will destroy your brains on your way to Mars. This guy, he's been giving mice a dose of about twice the amount that they would get if they were astronauts going to Mars. But that's not the main difference. The main difference is he does it at a rate 40,000 times as fast as they would get it. And that's real important. In toxicology, the rate at which you get a dose is critical. Okay, you could drink a glass of wine a night for your whole life, and it wouldn't hurt you. In fact, if it was red wine, it would improve your health. Yes.